All right, folks. In this lecture, we're going to look at what standard addition calibration is, why we would use it, and the two different types of standard addition calibration, a 2-point standard addition and a calibration curve standard addition. So let's first look at why you might need to use this more complicated type of calibration method. This is a way to cope with a reality that real samples that we want to analyze are typically occurring in a matrix that could be more complicated than what we would like to work with. So blood plasma or complicated environmental samples could have matrices that are hard to reproduce in preparing our standards, or we might not necessarily even know what all is in the matrix. So if we're worried that our matrix has chemical components in addition to the analyte that could either enhance or suppress the signal, then we need to account for those matrix effects. And the really convenient way to do that is with standard addition calibration. So with standard addition, we add small known quantities of our analyte within the sample matrix to each of our standards so that we can account for the matrix effects and cope with sample preparation loss. So the two general types of standard addition are called 2-point standard addition and calibration curve standard addition. And the first one, all we're measuring is one standard and one unknown. And we measure the signal from our unknown, and we measure the signal from our standard that includes the unknown in it. And I'll explain that more fully in just a minute. The other type is where we prepare all of our standards with the matrix that contains our unknown present in each one of the standards as well. So what we measure is a signal for all of our calibration standards, each of which also contain the unknown. And we plot it against the concentration of the unknown that we added as standards. So let's explain the process for 2-point standard addition. So for 2-point standard addition, what you would do is you would add a small amount of your matrix that contains the analyte into one volumetric flask and dilute it to the volume with whatever solvent you're using. And then you would add your same amount of your unknown matrix that contains your unknown analyte to a flask that is also going to contain a known amount of standard that you've carefully prepared. You know the concentration of the standard, you add a small amount of that to the flask, and then you fill it up to the volume of the flask to dilute it. And we're going to say that square brackets S sub F is going to be the final concentration of the standard once you added it to the second flask and filled it up to the volume. X sub F is going to be the final molarity of your analyte once you added it to the flask and filled it up to the volume. And X sub I is going to be the initial molarity of your analyte that you had at the time that you added it to each one of the flasks, but before you diluted it. Okay. So what do we do next? Now that we've got our sample prepared that's been diluted and our standard prepared that's been diluted and also contains our matrix and our unknown, we're going to measure a signal. In this example, I've measured absorbance of both flasks. So the orange curve on the bottom represents the signal intensity of the left flask that contains just our unknown in it that's been diluted. And then we're going to measure the signal intensity of the right flask that has our unknown, our added standard, and it's been diluted. Now, unsurprisingly, that has a higher signal, a more intense response, because it has not only the concentration due to the unknown, but also due to the added standard. Now, if we take the ratio of the intensity of our signal from just our unknown to the intensity of our signal with our unknown plus the standard added, what we have is a proportionality that we can start to work with mathematically. So the intensity of the signal in the left flask is going to be proportional to just the initial concentration of our analyte. And the intensity of the signal that has both analyte and standard is going to be proportional to the concentration of the analyte plus the concentration of the standard. Now this looks like it's got a lot of unknowns within one equation, but let's remember that the final concentration of the unknown here in the denominator is going to be proportional to the initial concentration of the unknown times the dilution factor. So what's the dilution factor? It's the initial volume of the unknown divided by the total volume once you added the unknown and the standard together. So let's look at an example and make sure we can understand how this is used. Let's suppose we want to measure ascorbic acid in orange juice. And so we take a 50 milliliter sample of orange juice and measure the current due to the ascorbic acid as 1.78 microamps. After that, we're going to mix a little bit of standard, 0.400 milliliters of standard with a known concentration, and we measure the signal again. Now the signal's gone up because we added more ascorbic acid than was originally present in just the orange juice. And the question is, what's the concentration of the ascorbic acid in the original orange juice sample? So let's just tackle this one step at a time. The first step is to find out what the standard concentration is in the orange juice after we mix the standard with it. So we're going to use this concentration. The final concentration of the ascorbic acid is equal to the initial concentration of the ascorbic acid in the standard times the dilution factor. So what's the dilution factor? We put 0.4 milliliters of our standard into the 50 milliliters of orange juice. And so now the total volume is going to be 50 plus 0.4. So after dilution, our standard concentration, S sub F, is calculated here. What's next? Well, what's next is we can think about that same logic for the ascorbic acid in the orange juice. The final ascorbic acid concentration in the orange juice that was endogenous, already present, is going to be the initial times its dilution factor, since we also diluted that by adding standard to it. So we'll have ascorbic acid final equals ascorbic acid initial times 0.9206, which is just the amount accounting for the dilution when by adding the standard. Next, we're going to do a ratio of the signal of the ascorbic acid to the signal of the ascorbic acid plus the standard added. Let's plug that in here. So if we look carefully back at the problem, the orange juice without any added standard had a signal of 1.78 microamps. And after we added standard to it, it was 3.35 microamps. And that ratio is going to be proportional to the initial amount of ascorbic acid to the total final amount of ascorbic acid, which was the amount in the orange juice after dilution, plus the amount of standard that's present. So this looks like one equation with two unknowns, but remember x sub f and x sub I are related. We, on the previous slide, decided that x sub f is going to equal x sub I times the dilution factor, and I can plug that into my equation here. And after that, it's just algebra to try to solve for x sub I, that initial ascorbic acid concentration. So I'm going to multiply the denominator by both sides. And here's what my algebra looks like after that. So 0.5313 times xi times 0.99206 is up here. And then this is our standard concentration times that ratio of signals. And if I'm carefully doing algebra, I can combine like terms on the left-hand side of the equation. And our x sub I minus x sub I times 0.52717 is going to equal this concentration of ascorbic acid. So now I just factor out the x sub I and solve for x sub I, and I find that the ascorbic acid concentration in just the orange juice before adding any standard to it is 0.00249. So that approach allowed us to measure the ascorbic acid without having to worry about the pulp and without having to worry about all the other components of orange juice in that really complicated orange juice matrix. All right, the next type of standard addition calibration we need to talk about is called a calibration standard addition, and that's where we create a whole calibration curve. Now, you know that when you create a calibration curve, you need a range of standards, and that's what's being depicted by the light blue color in each of these volumetric flasks. The far left volumetric flask has no added standard. The next one over has a tiny bit of added standard. The next one over has a tiny bit more. and a tiny bit more until we have a high concentration standard over here on the right. In each of these flasks as well is the same amount of our matrix containing our analyte. So in this example, I've put 5 milliliters of our sample into every one of our flasks in which we're preparing our calibration curve. We then dilute every single one of our flasks up to the volume and then create our calibration curve by measuring the signal in every one of these flasks. So on the x-axis is the concentration of analyte that we added, our standard that we added, and on the y-axis is the signal. Now you'll notice that our first flask still has a signal because even though we didn't have any added standard in it, it did have our unknown that was present in our sample matrix. So our calibration curve is shifted up in the y direction because of our unknown was present, and it's shifted over in the x direction rather than going through the 0, 0 point because it has that amount of unknown present. So how can we now calculate our unknown concentration? If we were to take this from a standard addition to a normal calibration curve, we would just have to shift this curve over to the right by the exact amount of our analyte concentration, since concentration is here on this x-axis. So if we can figure out what that x-intercept is, we can find out how much of that concentration would have to be removed in order to make this a normal calibration curve. So how do we solve for the x-axis? We fit our equation to a line y equals mx plus b and figure out where x is, what's the value of x at the point that y equals 0. So that's what's shown over here. If we have the equation y equals mx plus b for our calibration line, solve for x when y is 0, 0 minus b divided by the slope is going to be the x-intercept. So let's look at an example. Let's say we tried to measure iron through standard addition. We prepared our calibration flask, each of which had our unknown added to it. And then we fit this equation to a line. And if we look at the equation for the line, the slope m is 0.5815 and the intercept b is 0.0922. Now, if I were to try to eyeball or guesstimate what the x-intercept is by looking at this graph, I see that it's just a little bit before the negative 0.2 mark. So that's the amount, I'm guessing negative 0.18 part per million of iron that would have to be removed in order to shift this whole calibration curve over to a normal calibration curve. But rather than just estimate by eye, let's actually solve for it. So we solve for the x-axis by setting y equal to 0 and solving for x. And if we do that, the concentration of iron inside each one of those standards is going to be the absolute value of b, the y-intercept, divided by m. So just plugging in the y-intercept, dividing by the slope, I solve for the concentration of iron that was present in every single one of those standards, attributable only to our unknown. Now, once you've got that, how would you calculate an uncertainty? You can calculate the uncertainty in that concentration by using an equation that looks pretty similar to the other calibration curve uncertainty equations we've used. S sub y is the deviation of the points from the line of best fit. So S sub y you would get from a line est analysis in Excel. M is the slope, so you would know what that is. 1 over n is the number of data points in the calibration curve. So in this case, it's 1, 2, 3, 4, 5. You'd have 1 over 5 in this example. Y bar squared. Y bar represents the average Y value of the calibration curves. And X sub I minus X average. X average is the average concentration of the standards that you added, and X sub I is each individual calibration standard minus the mean squared. So it's a tedious calculation, but it certainly is manageable if you know what all of the terms mean.